Hello everyone. So today we will look into the conservation of orbital symmetry theory. Okay, and this particular theory is the one that is used in order to explain the stereoselectivity that was observed in the pericyclic reactions. Because when the pericyclic reactions were discovered and understood, scientists always wanted to understand why the configuration, like how the configuration of the reactant affected the product that is formed, and the reaction condition, how it affected the product that is formed. And they were very stereo selective. So that means, since we are talking about the double bonds, you will talk about the cis and the trans configured reactant, and how they were very stereo selective, that some of them gave only the trans product, some of them gave only the cis product. So how it was so specific in its reaction, scientists always tried to understood, and but they weren't able to explain how that was happening, or they couldn't using the theory that was known then, they were uh, not able to explain why there was stereoselectivity involved in these reactions. So the first breakthrough, or the important breakthrough, or the ultimate breakthrough that came, was by these two scientists, the R.B. Woodward and the Roald Hoffman. Okay, so both of them in the year 1965, they proposed the conservation of orbital symmetry theory. So that I have shortened it as COST. Please do not write COST in your examination, because this acronym I have not seen anywhere else being used in the standard textbooks. Okay, so please do not use this acronym. I have used it only for teaching purpose right now. So you please mention it as conservation of orbital symmetry theory. Okay, so it was these two scientists, and R.B. Woodward, you might have heard that he is a very good experimental chemist who developed a lot of total synthesis of natural products. So he was a very good experimental chemist. And Roald Hoffman, he was a good theoretist. Okay, so both of them together came up with this particular theory called the conservation of orbital symmetry theory. Now, you would be able to appreciate all these details more better when we talk about how it is applied. Right now, let me give you the definition of this particular conservation of orbital symmetry theory, which states that the in-phase orbitals overlap during the course of a pericyclic reaction. So that means during the course of a pericyclic reaction, the orbitals that overlap are in phase. Okay, so now you know that the orbitals, the molecular orbitals, they can be in phase or out of phase depending upon the signs that are present on the lobes of the orbital. Okay, so whenever two lobes are having are in same sign, like plus plus, they will overlap, leading to the formation of the product. So pericyclic reactions always happens when in phase or orbitals overlap. Okay, so this particular thing, that is the in phase orbital overlap, is actually deciding the configuration of the product that is formed. Okay, so that is why this definition holds, that is the in phase orbital overlap during the course of a pericyclic reaction. So this is the basic definition for this particular theory, that is conservation of orbital symmetry theory. So this particular theory has another definition which I can write it as the symmetry of the combining molecular orbital decides the reaction conditions as well as the configuration of the product. So apart from in-phase orbital, you will come across this term called symmetry. Some of the orbitals are symmetric, some of them are anti-symmetric. So depending upon whether the combining orbitals are symmetric or anti-symmetric, you will have the different reaction condition, as well as that is the factor that actually decides the configuration of the product that is formed. Okay, so this is another way of explaining the definition of conservation of orbital symmetry theory. Now, this particular conservation of orbital symmetry theory was actually based on the frontier orbital theory, which was actually proposed in 1954 by Kenichi Fukuyu. Now, you would be surprised that this particular theory was 10 years before proposed, and still it wasn't able to like kind of explain the pericyclic reaction. That is because this frontier orbital theory was kind of more mathematical in its approach, and it was quite complex to understand. So that is one factor why people were not able to realize these mathematical theory in order to explain these pericyclic reactions. And that is why that is not cost, but conservation of orbital symmetry theory is very, very significant work that was done. And for that purpose, Roald Hoffmann and Kenichi Fukuyu were given a shared prize for giving this conservation of orbital symmetry, and Kenichi Fukuyu for giving the frontier orbital theory, because on the basis of this only they developed this cause, that is the conservation of orbital symmetry theory. Now, R.B. Woodward wasn't alive during that time, and that's why he was not included among the Nobel Prize in the 1981. Okay, but he was given the Nobel Prize earlier for his work in the total synthesis of natural products. Okay, but for this particular theory, Roald Hoffmann was the one who was awarded the Nobel Prize along with Kenichi Fukui. Okay, so this is the theory that we are going to use in order to talk about the stereoselectivity in the pericyclic reactions. Now, in order to understand this theory and apply it to pericyclic reactions, we need to understand molecular orbitals and their symmetry. Okay. Now, molecular orbitals you might have already studied a lot in inorganic chemistry. Okay, where we dealt with the different types of VSEPR and VBT, and then you talked about the molecular orbital theory. So when you talked about the molecular orbital theory, you might have seen two different types of molecular orbital. One was sigma molecular orbital and another was pi molecular orbital. Now, in the pericyclic reactions, as I already mentioned, we have more of what you call it as the pi molecular orbitals, more of the pi molecular orbitals. Okay, so it would be better we study them individually or independently from the sigma bond, and that we can do because as you might be remembering, the sigma bonds are studied separately, and pi bond can be studied separately because they are kind of happening at two perpendicular axes. Sigma bond is happening along the internuclear axis, while the pi bond is happening perpendicular to the internuclear axis. So pi bond can be studied separately. So since we are dealing more with the pi bonds in the pericyclic reactions, therefore we will try to write only the molecular orbital concerned with the pi orbital in order to talk about the pericyclic reactions. Okay, so let's start with ethene. That is a compound with just one double bond. Okay, ethene is a compound which has only one double bond. So when we talk about the pi bond that is formed in case of ethene, we can talk about the overlap between the unhybridized p orbitals on the two carbon atoms. Okay, and each of these unhybridized p orbital is having one electron. Okay, now as you would do when the two atomic orbitals they are combining, they would give rise to two molecular orbital. One is a bonding and one is the corresponding anti-bonding. So since we are talking about the overlap between unhybridized p orbital, we are talking only about the pi bonds. Okay. So first, bonding means the in-phase orbitals, they are kind of sideways overlapping, leading to bonding pi molecular orbital. However, the one in which the phase signs are different, they are leading to an anti-bonding pi molecular orbital. Okay, so thus we have two different molecular orbital, Chi1 and Chi2, where Chi1 is the bonding molecular orbital and Chi2 is the anti-bonding molecular orbital. So here you can see I have written here Chi1 and Chi2, and since two electrons are there, we will start filling the lowest energy. So in the lowest energy itself, the electrons would be filled up. The upper energy is unfilled. So this is the molecular orbital for the ethene, which is Chi1 and Chi2. Chi1 is the pi bonding molecular orbital, while Chi2 is the pi star anti-bonding molecular orbital for a single double bonded system. Now in the coming video, we'll talk about the molecular orbitals for two conjugated double bonds and for three conjugated double bonds. And with that, we'll be moving on to how to use them to explain the stereoselectivity in various pericyclic reactions. Thank you.